Welcome to our talk about writing better code in Dylan. It's not the first time that the two of us, Hannes Mehnert, next to me, Andreas Bruck, my name, talk about Dylan. We did so before, but the last time we didn't really get into looking into the details of the programming language and all the features that make writing in Dylan better than writing other programming languages. And so this time around we want to go into detail there and explain what it's about and what makes it useful. So there are certain requirements one as a programmer has towards the programming language. It's a lot of them, some have to do with the language, some with the support around the language. A programming language should be powerful and expressive, so you don't have to write everything like 5 or 10 times. You want it to be universal. You want to be able to solve any problem in your programming language of choice. You want it to be easy to learn. It's no good if you have to spend years and years until you understand how to write good programs in a programming language. You want your code to be fast. You want your code to be easy to read. You want to have an open source implementation. You want to have tools available, libraries, etc., etc. So if you look at existing programming languages, they fulfill some of the requirements here, some of the requirements there. C, for instance, is really, really widespread, and it's pretty easy to find a library doing things in C. It's universal. People write all sorts of code in C. Performance is very good. Programs written in C are usually very fast. It's unfortunately not very powerful. There are certain expressive features just lacking in C, like the closures or real object system. You can do things to work around that, but it really doesn't cut the cheese. Of course, the support for tools in C is very good. Another language that comes to mind is Perl. Perl is pretty much universal. Well, not exactly everything is written in Perl. For instance, the Perl interpreter itself is written in C and not in Perl. So that's already a sign that it's not a universal language. It has certain niche markets. It's certainly powerful. It's very easy to write complex stuff in Perl. Well, it gets a little tricky if programs grow bigger, because at some point you start not to understand your language, your program anymore. It lacks certain abstractions, but on the other hand, you have lots and lots of libraries available. You go to CPAN, you find what you need, and you glue 2 or 3 pieces together. That's where Perl excels. Performance is good as long as you're manipulating strings. For everything else, it becomes slower. It's not easy to read. So the average Perl code looks like somebody has fallen on the keyboard. There's an open source implementation, yes. If Emacs counts as an IDE, there's an IDE. But you see, there are certain niches fulfilled by different languages. And our language of choice is Dylan. And we think it excels in a lot of the points named here. So it's not easy for a language to get to the point where you really say it's useful for everything. You have lots and lots of hype languages, like Ruby, for instance, is the latest hype, which does have some pretty nice features, but unfortunately, again, performance isn't so good. We do Dylan for quite a while now, and we have a track record of being successful with the programming language in contests. The ICFP programming contest is something we compete in every year, and it looks like odd years are lucky years for us, because we made it quite a number of times. And the programming contest, the ICFP programming contest, is very interesting because it is a real-world test for a programming language. The challenges in that contest are usually not, they don't have a proper solution. So it's not like your standard university test where you can get 10 out of 10 marks for solving the problem correctly, but the problem is so hard that there's no single correct answer, and you have the programs compete against each other. You have a limited time to solve the problem, so the expressiveness of your programming language is important. If you have to write everything 10 times over and over again, you just won't be able to finish your program in time. So in, this year, for instance, there were 168 teams. About 30 of them wrote in C, and of the 30 programs written in C, I think only 1 or 2 managed to even make it to the final round. So the other 29 crashed or produced no output or problems like that. They just didn't manage to finish the specification in time, let alone optimize it to compete.
There were also about 10 implementations in Perl this year, and all of them failed also. They thought quite hard about, on the mailing list, about how to exploit the others' code and send lots of messages, because Perl is good at string manipulation, and other languages like Python or Ruby aren't that good at string manipulation, and you had only limited time for each turn this year. So you had to answer in 5 seconds, and the Perl guys thought how to disqualify other teams.
Yeah, we didn't care about performance at all in that contest, actually. It just was fast enough to begin with. And yeah, that's one of the misconceptions many people have, that there's something like so-called scripting languages, which are high-level languages when looking at the language features, but who are notoriously slow to execute. So people think, yeah, scripting languages, high-level features must be an interpreter. Interpreters are slow. On the other hand, you have languages that are compiled, and those don't have that high-level features, so you have to work harder, but you have to work harder to get high-performance programs. And that's simply not true. It's possible to get best of both worlds, to get the features and the performance. And we've shown that. Yeah, the history of Dylan is interesting. It started out as a dialect of Lisp. Now, Lisp has been around, well, basically since the beginning of the computer era. And also the lambda calculus, which is the theoretical background behind Lisp, has been there for quite a while. Dylan is notorious for being the Lisp dialect which doesn't have the braces. It has a regular algo-like syntax. So all the people who don't like Lisp because of the syntax, try out Dylan, it might be the language for you. It started as a development at Apple Cambridge Laboratories for the Apple Newton. It wasn't used for the Newton actually because 1 megabyte of runtime code size was deemed excessive at that time. Still, Apple continued development of Dylan for their host platforms, for the desktop computer platforms. And together with them, both the Carnegie Mellon University and a company called Harlequin worked on the Dylan standard too. Yeah, Apple, most people probably know OpenMCL these days, Macintosh Common Lisp. The same folks who worked on Macintosh Common Lisp also worked on Dylan for Apple. Then one of the 2 or 3 open source Lisp compilers available is CMU Common Lisp, or these days SBCL, which is the same source code. And these folks developed at Carnegie Mellon University for the Dylan project. Actually, the project leader was Scott Fahlman, who's known for inventing the smiley. So he's been around for quite a long time. And, Harlequin is a very little known company, but they used to be, they're bankrupt these days, but they used to be the main manufacturer of LispWorks, a commercial Lisp compiler. So basically you had all those people with a Lisp background, and what they tried was basically doing the next generation Lisp. They had that common Lisp standard in the 80s, which was basically we tried to standardize what's there. If you ever looked at common Lisp, it's a very, very powerful language. It's probably the most powerful computing programming language on that planet. But it's very, very hard to learn. It's got in the standard 700 or so function calls, and it's got an ugly syntax. It pretends to be an easy syntax with all the braces, but if you look at reader macros and stuff like that, and it's ugly and hard to understand for a beginner. So they try to come up with a clean design. They overdid it a little bit. There are some corner issues which they shouldn't have removed from the language, but did remove anyways. I'll maybe come to that later. But mostly what they came up with was something very nice, a cleaned up version of Lisp with a nicer, more regular syntax, easier to learn and optimized for being high performance compiled. So these are basically the language features you find in the language. It's object-oriented. Everything you touch in the language is an instance of a class. This is also the case for all the so-called primitive types known from other languages. So in Java, for instance, you have that integer fundamental type with a small I, and then you have the big I integer, which wraps an integer into a class. You have to encapsulate and decapsulate all of the time. And if you ask them why they did that, they say, oh, there are performance reasons. In fact, you can show that you don't have to do that you can put everything into a class structure. So that's also a difference to Common Lisp. In Common Lisp, not everything is an object. There's the Common Lisp object system clause, but it's basically attached at the side of the Lisp standard, and you have fundamental Lisp types which are not instances of classes. So until you don't have that anymore. There's multiple inheritance. And again, Java is a language which dropped multiple inheritance. And if you write Java, you'll miss it. It's really so useful to just have some kind of functionality you mix into your class by inheriting from just another class. And for encapsulating behavior of classes in different abstract superclasses. And when you look at multiple inheritance in C++, it comes with a number of problems, because if you inherit the same class over multiple paths, you might end up having the same data slot twice in your class or not, depending on whether you do virtual inheritance or non-virtual inheritance, and the mind starts to boggle. And what's done in Dylan is so-called superclass linearization. It's also a trick borrowed from Common Lisp and the clause Common Lisp object system. Basically what you do is take all the superclasses and sort them into a list, into a linear list. And if you inherit from some class twice, the second inheritance path is removed. And that removes a lot of the hassle you have with multiple inheritance in other languages. It also removes lots of the performance problems multiple inheritance has. Multiple dispatch is a very peculiar thing. Most people who write object-oriented programs somehow think that object-oriented means we have classes, and classes consist of data and functions. And you call a function on a class, or you send a message to a class. That's what you know from C++ or from Java or from Smalltalk. But in practice, you don't have to. You can separate the functions and the data, and in Dylan actually classes encapsulate just data, and behavior and polymorphism of functions is encapsulated in so-called generic functions. It's pretty easy to explain what it's about. If you have A plus B, then plus is a function of A and B, and it's not natural to attach it to either A or to B. It's just a function plus. As in a regular language, you have verbs and nouns in a human language, and so you have in Dylan objects and functions. And multiple dispatch just means that for every possible permutation of arguments to a function, another method is selected. We will have an example later if that's confusing, but that's something to keep in mind. Multiple dispatch is a superset of the so-called receiver model of Smalltalk or C++. And it's more powerful, and in some instances it makes writing code much easier. Functions in Dylan are first class. That means you can put a function into a variable, you can pass a function around, and it's type safe. In C, you can have function pointers, which are a little bit like first-class functions, but not really, in that they are not type safe. But first-class function also means you can do funky tricks like map and reduce. We'll show them later. Types are also first-class, which is something you don't get in C++. That means that every class is an instance of the class, and you can pass it around and can do implement things like factories very easily by just keeping a hash table mapping from like protocol elements in your via protocol to the classes implementing the protocol. You can pull out the class and create an instance of that class without having to say the name, just by having a reference to a type somewhere. Dylan is dynamically typed. That's something, well, most people know the strongly typed versus weakly typed distinction. There's also a statically versus dynamic typed distinction, and it's actually two different things. Lots of people confuse it. Even the Python inventor Van Rossum confuses those things, so it's very common. Dynamic typing basically means that every runtime instance of an object knows its class. Basically, these days you have it anyways. In C++, since you have dynamic types and runtime type information, you have that in your types. It just doesn't feel very dynamic. You have it in Java as well, but again, it doesn't feel that dynamic because you have to specify the types of variables. You don't have to do that in Dylan. It's more feels like a scripting language, like working in Perl or something. You don't have to declare the type of a variable. And the variable doesn't have a type. It's just a binding to an object, and the object has a type. That's what it boils down to. So you write let I equals 23, and you don't care that I is an integer when declaring it. And that leads to you have to work less as a programmer. You have to write less code because you don't have to specify the type for your variables if you don't want to. But you also can make less mistakes. It's less work to change the types in your code. If you look at Windows code, for instance, sometimes the types of variables in the Windows API change, and then you have to go through all your code and change the type specifiers. And some people even use the Hungarian notation, so they have to change the type twice in all their code. And when you refactor your code, it just happens that the type of something changes. And the less changes you have to make to accommodate for that means less work, means less errors you can make. So dynamic typing is a convenience feature for programming, but it's also a feature of dynamism in your code. If you write in a statically typed language, you often start to emulate dynamic typing features by remembering some type information somewhere and then manually checking it. You usually notice in your C or C++ code when you start to pass around void pointers and then cast them back to some type that you really miss dynamic typing and want to have it. And it's Dylan does it the other way around. Metaprogramming is something here. I'm not sure if many people have heard it. It's metaprogramming or domain-specific languages. Basically, the idea is that you can change the grammar of your language to better accommodate your problem. We'll have an example for that later as well. So in order to work less, you describe the problem in a problem-specific language, and the programming language gives you a tool to change the language so you can develop your own language for describing problems. This comes in the form of macros. At the moment, Dylan macros work, well, they resemble C++ templates in a way, and that they don't work on text substitution, but they work on substitution on the parse tree. Or you can also say it adds productions to the grammar, so you can write your own if statement or your own while statement if you want to, or your own class declaration. That's metaprogramming. The last one is very interesting, optimistic type inferencing. If you've ever done any programming in ML or other statically typed functional languages, you probably know about type inferencing. It's that the compiler looks at your code and figures out the type of an expression. So if you write 3 plus 3, compiler knows, oh, I have a function called plus, the arguments are 3 and 3. I know that 3 is an integer, so I know that adding 2 integers will produce an integer as well. So the type of the expression 3 plus 3 must be an integer too. And what happens at that place in Dylan is that the compiler tries to do that for all as long as it can. So at some point you might have a completely dynamic case, like when the type of an object completely depends on user input, the compiler can't know it. But it tries to figure out the type of expressions at compile time and uses that information to optimize away stuff like type checks, stuff like function dispatch, and that's really where the high performance code comes from. So you can write your dynamic code and it won't be very fast, but you tie down your types a little here and a little there, and the compiler can predict a lot of things, and suddenly you have a fast program. That's also something you cannot do in C++. You cannot optimize away a vtable dispatch in C++, and basically Dylan can do that. Yeah, there were 3 implementations, I already mentioned that. Apple Dylan is basically dead. Apple had bad times in 1996. This was a very, very cool programming environment, and I was completely hooked. It was interactive. You could click on the features you have in Eclipse these days. Those guys had that 10 years back, including clicking on everything, including the debugger, and then ending up in the assembly of a function, and then going back from there into the source code. And interactive code execution, everything. It's a shame this is gone. Then there was the Carnegie Mellon project. It's a Dylan 2C compiler written in Dylan. And it's basically a batch compiler, so it doesn't have a lot of the power you really want from your environment, like interactive code executions, debuggers. But still, it's there, it's open source, and it's being maintained. And it's highly portable and generates efficient code. And it's something to play with. The third one, Harlequin, this one is very interesting because the folks who did that really have a lot of experience. You might have heard about Lisp machines. After Symbolics, the last Lisp machine vendor, went bankrupt, those people went to Harlequin. And so the people who worked on that compiler really, really knew their stuff. It's the people who wrote the Emacs or Emacs clone for the Lisp machine, the compilers for the Lisp machine, the garbage collectors there. It's a Dylan compiler which compiles native x86 code. And it's got an IDE, it's got a debugger, it's got a profiler. It's got interactive code execution, so you can type little lines of code and try it out with the code base. It got hot code updates, so if you run into a bug, you can fix the bug and upload the changed function into your running executable. Try it out again. And it used to be a commercial project and really was a big investment. And Harlequin also went bankrupt for various reasons. They have not only been doing programming languages, but they also did intelligence software and PostScript rasterizer software, and it was a big mess, and so they went bankrupt. A lot of parts were bought. The Dylan compiler was bought by the programmers who wrote it because no other commercial entity wanted it. And we're in the very lucky situation that those people finally decided to open up all the source code as open source. And we really have, it must be hundreds of person years into that code, about 1 million lines of code in our repository, which are now open source. It's so much code that with the 5 or 6 people in the maintenance project, we didn't even get around trying to compile all of the libraries which are there, and it's really a lot. And yeah, that's what we have been using. That's what we want to develop further. And basically, that's the powerful tool we want to have for our programming language. That's a little glimpse into the libraries which are there. So you have user interface, networking, regular expressions, persistent object stores, XML parsers, database interfaces, web server, mail server code, and probably lots of stuff we don't even know it's there. Dwim is an interesting point. If you ever done Common Lisp, you probably know Clim, the Common Lisp interface manager. And Dwim is done by the same person who did Clim before. So it's basically second generation Clim with most of the features of that. Yeah, that's finally a glimpse of Dylan code. After talking about all that, we're actually going to show you some code. So it has an algo-like syntax. It looks a little bit like Pascal, if you're used to that. Some people say that it's a little verbose, but the only thing really verbose about it, if you compare it to other languages, is that you have to write end. The alternative would have been doing the Python approach of using indentation instead of begin and end, or maybe another set of braces instead of begin and end, but in the end it doesn't really matter because I type fast enough, so it isn't a problem. And if you have 2 or 3 pages of code in a function, you actually start to appreciate that there's something at the end of a code block that's not just a void space, and you have to guess where it ends and go up 2 pages and look for the beginning, go down again. So I think it's okay. Dylan comes with a lot of flexibility in choosing names for identifiers. So for instance, it allows dashes in identifiers, which really makes the code much easier to read, because usually you start to use underscores and it's straining on the eyes to use underscores, and it's much easier to read with a dash in the middle. There are some naming conventions, like using angle brackets around type names or asterisks around global variables, predicate functions and in question marks, etc. These are all only conventions. It's not part of the syntax. Yep, dynamically and strongly typed. It's, I already mentioned that it's very important to distinguish the two. Strong versus weak typing basically just means that in a strongly typed language, you don't have a way to work around the type system of your language. You cannot pretend some object, some integer is a pointer or something like that. So in a strongly typed language, lots of security relevant bugs just can't happen. Whereas in a weakly typed language, you can use a cast and cast around, or maybe just do an addition and it will magically cast behind your back. So Dylan is strongly typed in the sense that you cannot circumvent the typing system, but it's dynamically typed, and that runtime instances of objects have types, and bindings, what other people would call variables, don't have types or don't necessarily have types. So it feels like a scripting language in typing aspects, basically. I already mentioned the object system as well. It's class-based. The opposite of class-based would be prototype-based, like done in JavaScript, which stole the idea from a language called Self. So in Dylan you have classes, and every object is an instance of a class. And that's what a class definition looks like. There is a lot of syntactic sugar in such a class definition, but the point in that is that you usually don't have to write a constructor. You get around writing a constructor because all the usual cases are already covered. You see there's a square which inherits from a class rectangle, and what C++ would call a member, or other languages would call a field, is here called a slot. And there is a type declaration for the slot named X, which is of type number. So the two colons say here's a type. This is one, the type is actually optional. You don't have to write it. If you do write it, the compiler will check the type for you. So it does a type check on assignment. And it also knows that if you call a getter for that slot, that the object has a type number, uses that for optimistic type inferencing. I have a default value, which is 0. And then there's an init keyword. If I create an instance of a square, and usually a square is, an object is instantiated by calling the function make, I can pass an init keyword x or y and specify a number there. And there's also another slot, and you see it also has a keyword, but it's got a required init keyword. What that means is that if you don't pass that init keyword and don't pass a value for that slot, then the system will refuse to create an instance of the object. So basically what you defined here is if you create a square, you can pass an x and a y coordinate for placing the square, but you have to pass a slot, pass a width, which must be a number. One of the slots is constant, which means that no setter is generated. You can only set the object on instance creation. And that's also something the optimizer uses. So in this case, it knows that slots x and y are initialized. They're initialized to 0. So the slot cannot be uninitialized. So you don't have to include a check when accessing the slot of that object if it's initialized or not, because it always is. The same for the required init keyword. And also knows that this width slot is constant and can use that information for moving around expressions in your code for optimization, pulling stuff out of loops, etc., etc. I already mentioned keyword arguments. Here is an example of a function which has a keyword argument. So the function describeList, you always have to pass it myList, but optionally you can pass it a keyword argument verbis ? So you can say describeList, some list, and then verbis ? true, and then the code is executed, but you can leave it away. So that's a way for having optional arguments. Again, in C++, you can give default values to function arguments, but you have the restriction that you can only leave away the last argument. So if you have two optional function arguments in a C++ function, you only want to pass the second one. You cannot do that because you have to pass the first one before, and you have more flexibility with those keyword arguments. Yeah, higher order functions. I already mentioned that functions are first-class types in Dylan, and higher order functions are functions operating on functions. And this usually allows to write very compact, very efficient code. Anonymous functions are one feature. You don't have to name a function, but you can create a function on the fly using the method statement. So the function on top is actually a function returning a function. If you look at the function body, it returns a function which does a little computation and accepts an argument x. And what you also see here is a concept called a closure, which is basically you create an anonymous function, and that anonymous function refers to other information, and basically the method makes a copy of that information and puts it into the function as well. So it's more powerful than a function pointer because it's basically a function pointer with additional attached data. So for instance here in that, the make linear mapper function takes two arguments, times and plus. And those are referenced inside the anonymous function that's generated there. And every time you call make linear mapper, it creates a new function, returns basically a pointer. There aren't really pointers in Dylan, but it returns a pointer to the newly created function, which remembers the values of times and plus. So you can execute the code, which you see in the bottom here. The defined constant times 2 plus 1 calls the make linear mapper function. And so the constant has a value of a function that takes one argument. You can call that, pass 5, and get the desired result. This is very, very useful for creating stuff like callbacks in a user interface. You have a graphical user interface, the user presses a button, and the moment the button is pressed, some callback is called. What you often see is in, say, C, that the user can set a callback, and then there's an additional data parameter, which is passed to the function that the user has specified. And then you can stuff all kinds of data for doing the work into that one single data pointer. And what you usually do is create a structure and then cast it to a void pointer and put it in there. And when you pull it out back, you cast it back to the function you expected there is. But that's not very convenient, and it's basically not type safe. At the moment you start doing conversions to void pointer and back, you risk making a mistake, and that means risking a crash. So a closure is a type safe way to do the same thing, to basically pass arbitrary arguments to your callback function you create on the fly. It's the function class, it doesn't have a public interface. If you look at it from the inside, you'll see that a function has a number of entry points, which are basically code addresses. Usually you have interior and exterior function entries, which do type checks or do not type checks, and the compiler can leave away the type checks if it can prove it's safe. You usually have a subclass of function for closures, which then references the list of variables you referenced to get at the data. So, but it's nothing you ever see as a programmer. It's just behind the scenes. There are other convenient functions that, something you should mention, if you have ever used Lisp, you'll know lambda expressions. And basically, what's called lambda in Lisp is called method here. It's the very same thing, just a different name. And the Lisp people call it lambda because of the lambda calculus. And in Dylan, they decided that most programmers instinctively know what an anonymous method is, but have never heard in their life about lambda, so they changed the name. You can do other interesting things. Curry, for instance, takes a function and an argument and returns a function where that single argument is already on the list. So you can say curry von plus and 1, and that's an increment function because plus takes 2 arguments. If you say curry from plus and 1, one of the arguments is already put into the closure basically. Reduce can be used to operate on a list and basically call the same function for every element in the list in succession. Map does something very similar, which calls a function for a list, for several lists of arguments. So it takes the first argument and takes the first element from all the lists and passes it to the function and then to the second one. And so instead of writing 5 lines of a for loop or something, you usually get around with just a reduce and a curry and maybe an anonymous method to do a lot of things.
And you don't have to think of off by 1 errors in loops, because you simply use map and don't have to count the size of the list. Yeah,
it's less typing, less opportunities to make errors, etc., etc. Yeah. You can call C functions pretty easily. That's how it is done. You import a header file. That's not standard Dylan, but it's something that works. Generic functions. It's what I mentioned when talking about multiple dispatch, that Dylan separates the idea of classes from the idea of functions. And a generic function is basically a collection of so-called methods for certain sets of parameters. So that's a very simple example because you only have one parameter that's passed to the method double. Can either be a string or a number. And depending on whether I pass a string or a number to a function called double, one of the two methods is called. That isn't more powerful than the other approach yet, with one difference. I don't have to think about all the functions I could possibly want to call when writing down the class definition. So as a user of some library, I can write my own generic functions operating on somebody else's classes without having to change his class definitions. But the real power is when you pass multiple arguments to a function, and the right method is selected by looking at all the arguments that are passed to the function. So in that example, we have a inheritance structure for vehicles which knows about cars and trucks, and I have inspectors and I have state inspectors. What happens is that when I call a generic function, it chooses the most specific methods. That means that method which most closely resembles what I actually passed to the function. The next method calls the less specific method. So in that instance here, the most generic case is a vehicle and an inspector. And if the vehicle is a car, it first calls next method and then additionally performs additional checks. And the same for trucks. And you see that you can basically write down a method for all possible permutations of arguments passed to that function. So the usual explanation why that is useful is when thinking about the sex function and male and female objects. When you start thinking whether sex is a function of male or a function of female, which then gets passed the other one as an argument, you start to realize that doesn't make sense at all. And you also start to realize that make love of man and woman is something entirely different than make love from man and a man, and that again is entirely different from make love from a woman and a woman. And so the whole concept of the way object-oriented programs are written in C++ or in Smalltalk, it just isn't powerful enough to express all the ideas we have about how things work in real life.
There's a question. The order in which the next method calls are executed, is it well defined, or is it just by accident? Or?
Yes, due to the superclass linearization, you have a single list which type is more specific than another type of a class. So the next method calls the next specific methods. There are corner cases when you have two arguments and both are equally far away from the actual type.
If you had a method inspect vehicle which would take a truck argument and a state inspector, and we would run the next method at first, would it call the inspect vehicle on the car and the state inspector, or on the truck and the inspector? Or is it by chance, or is it it's possible to define an order, but Dylan takes the default order?
It's not by chance, it's well defined. There's a linearization algorithm which is specified for, which defines the order. But basically, this is such a corner case that it's probably not a good idea to rely on any specific ordering in that case. So it's better to use it if you really know what's going on, instead of, or if you don't care whether the one or the other one is called first. So in that example, for instance, it doesn't make a difference whether the seatbelts are checked first or the cargo attachment is checked first. It's the same, but it's well defined. Okay, That I already mentioned in the optimistic type inferencing. So in the first line, let defines a variable. So let C equals A plus B, defines a binding C and assigns it. And I can leave away the type because it's dynamically typed, and the value that's computed on the right-hand side is what has a type. But I can optionally specify a type for a binding. And what happens then is that a type check is done. So at the moment of assignment, it checks whether the type is still okay. And it also uses the type for type inferencing purposes to speed up the program. So if for instance, you add two numbers, in Java, the argument is we have that fundamental type integer and then a class integer, and if you want to be fast, you have to take the fundamental type. And but what basically happens here is that if it knows that you're talking about an integer, it doesn't have to do the generic function dispatch and finding the right method for adding two integers, but actually calling the right method right away. And it then boils down to a single assembler instruction that's emitted in your code instead of all the dynamic overhead that's there in the generic case. Okay, macros. That's a. I don't think I go into detail and explain everything you see there, but if you look at it, the general structure is that you have a pattern, which is in the upper part of the macro, and a replacement for the pattern in the lower part. And the stuff starting with question marks are pattern variables. So with open file is something you write literally in your code. And things starting with question marks are variables, and it's checking the type of the expression you write there and binds it and generates a replacement. So what you see here is that a convenience macro which takes care about closing the file if you leave the scope of the block. And it's very easy to write stuff like that to extend the language and to make sure, for instance, that your files are closed when the function is over. Macros in Dylan are very powerful. So this harmless little for loop here, you probably have that in other languages as well, that you can write for variable in my container. But the difference with Dylan is that for is implemented as a macro, and it calls a function called forward iteration protocol on your collection and gets handed back a set of higher order functions for iterating over the elements in the list. So if you expand this macro, what really happens behind the scene is this. So it calls a generic function forward iteration protocol, which knows about how to iterate over your collection, whether it's a list or a vector or an array or a hash table or whatever. And then uses those iterator functions to iterate over over your collection. But of course, this isn't fast at all if it does it like that. But then, as next step, the optimistic type inferencing kicks in, and it starts inlining all those little tiny functions and type inferencing, etc., etc. And if you run it through the CMU compiler, which generates C code, what you end up is something like that, which is a while loop, and then you have that state equals state plus 1, and a expression which pulls out the element out of your vector. So really, it's very simple to use. It's very powerful, and it's still very, very fast. So and that's what making writing in Dylan a breeze. So other stuff we have is type unions, and one important type union is, do we have that? We have it here. The false or type union. You often have the problem that you have to reserve one special value as I don't know, or I don't have an answer. Lots of function in C return -1 for an error. But you sometimes have cases where you want to return all possible values of integers and still want to be able to signal, I don't know, haven't computed that yet. In that case, you can use a type union with false, for instance. So you can say, my function returns an integer or false, and that's also a type in Dylan. We have non-local exits. Non-local exits are, well, it looks a little bit like goto. You have that block statement here, and in the brackets you see return, and in the middle it's actually calling return. And what it does is it jumps out of the block into the cleanup clause or behind the return. The interesting difference is that return is a first-class object. It's a function you can call and you can pass around. It's basically a continuation, but it's not a full continuation. It's a lexically scoped continuation for people who did scheme. We have exceptions. That's also something that's a little bit different because in C++ or Java, when you throw an exception, what happens is that the stack is unwound and then your handler is called. In Dylan, it's the other way around. Your handler is called and your handler may decide to call a non-local exit, or it might fix the problem and tell the program to go on. So one of the usual cases is you discover the disk is full, and instead of aborting the operation, then telling the user that the disk is full, and then somehow remembering what the state was to allow him to go on, just pop up a dialog, say, oh, the disk is full. If you free some space, now I can continue, or if you wish, I can abort. So this allows you to be a lot more flexible with dealing with exceptional situations and with establishing protocols between the place where you know how to deal with the problem and the place where you discover the problem happens. Okay, we have a couple of links, and how much time do we have left? We have 5 more minutes left, and we want to show you a little real-world application that Hannes has written in Dylan called Buddha, which is used on that very Congress to manage the network, the IP network.
Yes, well, first start with Buddha, we needed a DNS and DHCP management interface. We used last year a Perl script using an SQL database, and which wasn't really handy to be evaluated more. So I wrote Buddha. It is a web interface where you have a list of VLANs, a list of zones, some hosts, some networks, subnets in networks, and recent changes. You can add VLANs, you can add other things, and you can generate DHCP config and DNS config from the database it has. So now jump into the code. I've started nearly looking at Ruby on Rails. Ruby on Rails was in Ruby, and I don't like the Ruby syntax. I can't read it. So I started with an XML macro where I wanted to write that code. And it should generate that HTML thing, or that XML thing. So that's a macro. That's meta-programming stuff. We have a macro with XML, which has on the left-hand side with XML and some element, and produces the first element. Then we have an auxiliary rule set of the element, which does the actual expansion.
I think the point here is that you see how the macro system is used to come up with a specialized language describing XML documents, and which allows to mix XML and code to execute to generate the XML.
Okay, the next thing I came up with was a macro for a web class definer. I wanted to generate all the user interface code, the formulas, the edit fields, the checks of the added fields and so on dynamically. So I defined a macro web class, which generates a class and some other things. So a VLAN has a number. Well, that's an integer. It has a name and a description. And that little code with the macro I wrote generates, for example, that one, the formula to add a VLAN. So you can enter a number, a name, and a description, and it added VLAN 99. All those text here, there I use the exception handling of Dylan. It was quite nice, and it wasn't much code to write. I can show it. Or well, here, for example, it generates the added form, the formula. It uses again the with XML macro and do some things, go over the slots and return default values and so on.
So again, the idea is that as a programmer, you never ever want to write something twice. So if you want to add another thing for your web application, you don't want to describe it twice or 3 times or 4 times or 5 times by writing a template for showing all the instances, by having a template for editing, by having a template for this and for that. And using the tools of Dylan, it was possible to come up with that define web macro form, which does everything behind the scenes. If you want to add another type of network objects you want to manage, like say IPv6 networks, it will end up being something like 20 or 30 lines of code, again, which calls that macro. And it comes up with editing facilities where you can edit the slots and manage them and delete them, show them. And that makes programming easier because you only have to write it once. You cannot make it wrong the second time around.
So I have to specify the check method, which takes a VLAN and looks if the VLAN is okay, if it's not in use, the VLAN number, and so on. And well, that's about 15 lines of code, and it works. And it is used on several places. I also wrote a generic interface for editing all this stuff. So here everything is generated automatically. It has lots of things.
Mm-hmm. So unfortunately we are running out of time. Yeah. We would like to really would have liked to give you a deeper look into how the Buddha works. But I think one thing we should show is the way that the data storage is done. It's using the Dylan object-oriented database, which is a persistent database. And the code for saving and deleting is, basically that.
That one is for restoring the database. I just make a dude object, and the file name I get passed. It's in the global variable directory and file name. Then I define a local binding Buddha to dude root of dude. Well, dude root is a function on the dude object, and I close the dude and then set my other global things I use, and I use a simple versioning system. That's a restore, and the save is here. I do it in a thread. I save every 5 minutes. I just do a while true loop and use a file name with a version number, make a dude object, this time as direction output, not input, so it puts something out, set the dude root, commit it, close it, increase the version number, and sleep for another 5 minutes.
So basically in 5 lines you can write arbitrary data structures to disk and read it back. Okay, our time is over. We'd like to thank you for your attention, and